Hi, this video is about the famous wave equation in physics. Just as cheeseburgers are to McDonald's or fried chicken is to KFC, waves are an essential part of our world. Our world would not make sense if there were no waves. Waves are just everywhere. They do a lot of things in our world. And if we want to understand how our world works so that we can solve problems in our world or design new technology, understanding waves is a basic foundation that we need to start with. And one of the ways that waves work is the way that they carry energy. The speed that a wave travels through some medium depends only on the medium itself, only on the properties of the medium. Some media snap back in place faster, and therefore they can pass on the wave more quickly. Right? So think like a garden hose, and you shake a garden hose up and down, the wave goes down the garden hose. But if you were to tighten that garden hose and then try to shake it, the wave travels a lot faster because the garden hose snaps back in place a lot quicker after you disturb it. Now, one of the key features of waves that's a little bit surprising to, as you learn about this, is that the amplitude of the wave or the frequency of the wave does not actually make the wave go any faster. So if you have a tuba and a trumpet, both playing, different notes, the tuba's playing a low note, the trumpet's playing a high note, this one's got a big amplitude, little amplitude, it doesn't matter. Those waves will travel at the same speed because the speed of the wave depends only on the medium that it's traveling through. In this case, the medium for a sound wave would be air. So if the air is the same for both of those sound waves, the speed will be the same as well. Now, how do we measure speed in physics? This is one of those basic equations. Speed is measured by distance over time. So like miles per hour or meters per second. So speed is distance over time, but for waves, we can actually measure distance and time a little bit differently using different language. So instead of distance, we can talk about the distance between two repeated points on a wave called the wavelength. So for one wave, the distance is the wavelength. And for one wave, the time for one wave is called the period. So speed is wavelength divided by period. Now I'm going to rewrite this just a little bit to make it kind of, instead of wavelength divided by period, I'm going to put 1 over period times the wavelength. It's the same thing. I'm just kind of separating out the fraction here. And I did this because 1 divided by period is actually equal to the frequency of a wave. And this is a measurement we use more often than period when we're talking about waves. So this is a little bit more useful for us. So the frequency of a wave multiplied by its wavelength will give you the speed that the wave travels. And written in shorthand notation, we have V for speed equals frequency times wavelength. This is known as the famous wave equation in physics. And this wave equation is so important because it communicates a lot in just 3 letters. And this is, you kind of have to know the backstory behind waves. The backstory is, since the speed is not influenced by the frequency or the wavelength, that means if you change the frequency or the wavelength, they influence each other. So increasing the frequency makes the wavelength shorter. And let me try to illustrate that here. So I've got frequency times wavelength. This is a small frequency and a big wavelength. Okay, so I've drawn it here. This is a low frequency with a long wavelength. So measured from here to here, that's a long wavelength there. Multiply these two together, you get the speed. But over here, if it's still the same medium, the speed would be the same. So if you, instead of going at a low frequency, if you did a high frequency, the wavelength would have to get smaller as a result so that the speed stayed the same. So you would have a high frequency and a shorter wavelength. This distance right here is much shorter. So for both of these, the speed is the same. If you multiplied frequency times wavelength, both of these would have the same speed. So increasing the frequency causes the wavelength to get smaller. So I wanted to illustrate this in one more way. I like this illustration because it helps me remember this process. Imagine that you go running on a treadmill, and in order to, exercise your core a little bit more, you wear a weighted exercise belt as you're running. Okay, so you're running on the treadmill. Let's say you're going at 5 miles an hour. It's pretty fast, you got to keep up with that. Let's say that this little exercise belt falls and drops to your ankles. Suddenly, you don't have as wide of a step length anymore. And so in order to keep going the same speed, the treadmill hasn't slowed down. In order to keep going the same speed, what do you have to do? You're going to have to take a lot more steps. Your stride length is a lot smaller because of the exercise belt. And so because of that, you're going to take a whole lot more steps in order to keep going at the same speed, if it's even possible. So I tried to illustrate that over here too. The step frequency and the step length are normal before, but dropping that little belt to your ankles causes your stride length or your step length to get really, really tiny. And in order for the speed to not change, you have to have a lot more steps. You have to take a lot more steps in order to keep going at the same speed. It's also the same idea, like if you've ever, like I'm kind of short, so if I walk with somebody who's really tall, I might have to take more steps in order to keep up with them going the same speed because wavelength is smaller, but the frequency has to go higher in order for me to go the same speed. So that's the wave equation in a nutshell, and that's all I've got for you in this video. Remember, humility is not thinking less of yourself. It's thinking of yourself less.